This program is brought to you by Stanford University. Please visit us at stanford.edu.
You in for a good ride? Yeah. I've had them all in class before. I can't believe they're coming back for more. Red, this is what, fourth time you've taken this class? Trying to get through it? Good, okay. You're in E20, and I hope you can find yourself up here somewhere. I know we have some MS and E people. Yeah, right here. See, this is where you guys end up. Not here, not with the dollars, over here in psych after the burnout. So here we have, what are your interests? Entering freshman, party, sociology, need no sleep, computer science. This is your life unfolding before you. But if you're interested in sewage, you go into CE, civil. You're interested in dirt. I don't know what MSME means, but if you're interested in nothing, you go into IE. Bombs, nuclear engineering, grease ME. It all ends up in senior burnout, an internship, you're still burned out, go to psych, 5-6-year program, more parties, job offers, grad school, big, huge loop here, and then maybe some money. And I just want to get this out of the way right away. This is all about money. I just want to let you know here, chemical engineering, 2007, 59,000. The only one that beats us out is petroleum engineering, only because nobody goes into that major anymore. So they can put any number here they want, it's meaningless. So I just want you to know that you're in here for all the right reasons. So let me tell you a little bit about the class in the interest of full disclosure. Well, first of all, my name is Channing Robertson. You probably saw that written somewhere. I first started teaching this class in 1970, about when you guys were born, or maybe a little before. And I have to tell you that this is going to be a special year because this is the last time I'm teaching the class. So you guys got in right under the wire. So this is why I'm feeling pretty jazzed about this. Not that it's the last time, but it's. I want to make sure it's a good experience for all of you. And we have a syllabus. We don't have a textbook. And I can tell you, when you fill out the course evaluations, you will complain that there's no textbook. And so I'm telling you there's no textbook, so you don't have to complain about the fact that there's a textbook. Why isn't there any textbook? There's never been a textbook written good enough for this class. And so I wrote one. But it's not good enough to be published. So you can purchase this for $20 from Babette in the chemical engineering department. And that's in Stauffer 3, which is a building you actually walked by to get here unless you came from the mausoleum. And so stop by and get your syllabus. The nice thing I think about the syllabus is, number one, everything I put up here is in the syllabus. So this is not a copy fest. It's not how fast you can copy from the board into your notes. You can take notes in this. You can read the daily. You can read whatever you want. But it's all here. Now, one of the things about not having a text is you really do need to come to class. So if you're the kind of person that comes to the first class and then never shows up again, you're going to be at a real disadvantage in this class, because if I didn't need to be here to do something for you, then I could have actually videotaped this class in 1970 and just turn it on and leave and go mint juleps in the Bahamas. And so there is a purpose to this, and part of the purpose is I like to think of my job as passing on to you not a bunch of content, but perhaps some of the intuition about how chemical engineers think and approach problems and solve them. You'll have plenty of time to solve problems in this class. There's 8 problem sets, essentially 1 a week. There's 2 midterm exams and a final. And we have all those dates, and I'll show you when they are, so there's nothing will sneak up on you. You can make all your plans for the quarter. So bring this to class each time, and it's in a nice sort of spiral bound, so it works for you, and you can use this as a platform to take notes on. Now, we also have mounted on CourseWorks some PDF files, and I'm just showing you them right now. Although Max, I need to make this smaller. Somebody help me. Zoom. I'm on the right track.
Get a Windows computer.
Theo, you're now getting a B in the class, and you're not going up. How about Fit Visible? That's worked, isn't it? You know, how about full screen mode? Hey, that's not too bad. So anyway, these are the objectives of the class, which you can read, but I do want to introduce not only myself, it has my office in it here in the Keck Science Building, but also my office hours Wednesday after class or by appointment. I would encourage you to take advantage of and make an appointment. You can call that telephone number. A lady by the name of Barbara will answer the phone. It's up in the School of Engineering Dean's office, where I hang out most of the time in Terman. You can come up and visit me there. Most students find coming to the dean's office is a horrible experience, and so nobody comes, but I would encourage you to come. We have a head TA, Max. There he is. Max, say something about yourself, Max.
I'm Max Greenfeld. I'm the head TA of this class. I'm a third-year graduate student in the chemical engineering department, but I work for a biochemist, so I spend most of my time doing biochemistry.
So Max is the head TA, and you can remember his email. It's really easy. It's themax@stanford.edu, after Mad Max, that famous cult movie that maybe some of you have seen. Now, we have teaching assistants. We have 4, well, Max doesn't count because we've already counted him. So in addition to Max, there's 3, 4, 5, 6, 7, 8 teaching assistants. Now, who are these people? These are people that took this class and passed it. Not necessarily the first time, but ultimately they did pass it, and they form what is known as the peanut gallery. And they sit back up there in this little group. They are there to help you. As you can see on this handout, and by the way, this is on the web, so you can pull it off of CourseWorks. We have their emails, and you can see that there are office hours being held on Sunday, Monday, and Tuesdays of every week. And where they're held is shown in location and the times they're held. There's no excuse on your part not to take advantage of these people. Go see what it is they have to offer. I'm not sure. But it's got to be something worthwhile to spend some time with them. And they will help you if you have problems on your problem sets. Go spend time with them. The whole purpose of this class is to enable you to be successful. This is not a weed out class. This is not a class where we try to develop, a market for Prozac. We want you to have a good time. But we do expect a little bit of performance. And by the way, you'll see these microphones and things around the room. I guess for the Smithsonian, they're taping this class for the last time that I'm teaching it. And so if I say something, that may be a joke, please laugh. Because, this is like, these people are going to be watching this, from, in Lower Slobovia. So take advantage of the TAs. So what I'd like to do is introduce the TAs to you. So one at a time, stand up, tell them who you are, where you're from, why you're here.
Chemie, and I'm doing this because this class is the reason I chose Chemie.
David, I'm a senior Chemie, and I guess as a senior, this is my last quarter, so I have some time, so I want to help you guys out.
Hi, I'm Shashank. I'm a sophomore Chemie, and I really enjoyed this class last year, so I wanted to do it again without having to do the work.
Hi, I'm Sherry. I'm a senior Chemie, and I think it's really fun to meet you guys, and also I'm a senior, so it's not like I have anything better to do.
Hi, I'm Rudy, and I'm a senior in Chemie, and I'm here because Channing tells great stories.
Yeah, he didn't hear him the first time, or he didn't get him. Anyone else? So Sasha, we need some time and location for you, it looks like.
Yeah, I was going to do Monday 7 to 9, unless you want 2 TAs on Tuesday night. Just because the problem sets are due Wednesday, and I know everyone works really far ahead.
Right. Sounds like Tuesday night for Sasha. We'll load that in, and once she selects it. So course reading, we have the handouts in the syllabus that I'll be giving you. You have your own lecture notes, and there's library references. So on the library references, you'll see that we actually have a number of references in Swain Library, the chemistry and chemical engineering library, that will be there for you to use. And as I'll show you in a few minutes, each lecture is keyed to a number of references that you can go look into. I have noticed, because I asked Grace Basinger at the end of the quarter how many times these references have been looked at. Generally, it's a number less than 0. But it's there for you to use if you so choose. Now on Mondays, after class, there's a problem session. So one of the issues that have come up in past years is that we don't work enough problems or example problems for you. So the Monday session after class is simply one or more of the TAs will come in and work example problems and take you through them. So that's a skill building exercise. It's something I would encourage you to do. And it will obviate any of you who have the urge to say in the teaching evaluations, there were no problems worked. Because there are problems now worked. I'm responding to prior evaluations where I was said this is a cheesy class because there's no problems. So now there are problems. Special events. We have a couple field trips. You remember in high school, I used to like movie day. You know, you see the projector all set up. You probably didn't have projectors when you went to school, but the projectors, I think, has film in it, and the teacher would show so I could snooze out. So we have field trips in this class. You might say, well, Stanford classes don't have field trips, but we do. And one of them will be to the blood center. One of the first things we're going to do is design an apheresis machine. And after having designed it, we're going to go over to the blood center and see them in action with people hooked up to them. You can press on the tubes and see what the people do, like that. And you can see all the signals they have for when people step on the tubes. We ride bikes to the field trips. And I have people who say, I don't have a bike, or I have a bike, I don't know how to ride it. I mean, I get all kinds of excuses. I don't care what your problem is, you get there. If you can run fast, you can get there. But it's over in the Stanford Industrial Park, and we go on bikes after class, and I'll give you the dates of those. Have someone who does have a bike, ride on the back of the bike with them. Hire someone to take you there, whatever you need. Everyone knows how much does everything count? Well, here's what it counts. 30% for problem sets. I'm a real believer in skill building through problem sets, so you get quite a bit of credit for doing that work. There's an exam on April 25th and another on May 16th. They each calculate are 20% of your grade. All the exams in this class are open book, open notes. I prefer you not bring other people with you to help you, or bring in encyclopedias and stuff, because it's not going to help you. The reason it's open book and open notes is because I'm going to have you think and synthesize and put things together. You're done working the odd problems at the back of the book. That's high school. Okay, so I'll give you problems that are probably overspecified, too much information. On one exam, I put the mass of the moon. Some student actually put the mass of the moon in the problem, thinking that it was required because I gave them the mass of the moon. didn't work out well for that student, and he's now in MS&E. But other than that, it's, I don't, sorry, I just, I love MS&E, I love you guys. Exam 3 is 30%. It's really just sort of a glorified midterm, although you have 3 hours to work instead of 1 hour. And it's cumulative. People say, does it build? Yes, it does build because you learn things at the beginning of the class that you need at the back end of the class. So this isn't one of these where you go brain dead after you've had your first midterm. You don't have to remember any of that anymore for the rest of your life. You sort of do have to, this is cumulative, okay? So I told you we have a web page up under Courseworks, and we have grading groups. And so when you want to come and complain and sort of scam for 1 or 2 more points, you'll know who to go see because you'll know who graded your problem set. So I do have one thing. If you come in scamming for points, the TAs have the option to look through the rest of the problem set to take away points in case they felt they were too generous. So it's not necessarily a win-win proposition when you come in. And by the way, don't turn anything late in this class, unless you've been hit by a bus and you're not conscious. That counts. But if you've been hit by the bus and you are conscious, you got to get the problem set in on time. So otherwise, we start docking you massive points, and that's no fun because you need the points. All right, so let me go to, if I can, Max told me this would be just seamless. And of course, Max doesn't know anything. And so, here. Yes, I can see that the window's too big. And I just, another B. All right. So up on the website, you'll find every class, what the lecture's about, and if you look, you'll see these superscripts right here, 1, 2, 3, 4, 5. At the end of this, you'll see that those refer to books in the library. Library, that's probably a new word for you. Google is not a library. It's the largest collection of uncertified information on the face of the earth, but it's not a library. And so you can go to a real place for real information called a library and look these up if you have some questions about the content of that particular lecture. Here are the handouts, or this is where we're going to be in the syllabus, so you know where to turn. This is when homework number 1 is given out. That's today. This is when it's due. This is the field trip, their first field trip on Monday the 14th. So there won't be a problem session after that class because we're going to be on the field trip. Our other field trip is on May 19th, again on Monday. And we're going to go to the Artificial Kidney Center over at the VA hospital. So one of the things we're going to do in class is design an artificial kidney. And then we're going to go see one and see the people hooked up to the artificial kidney. You'll be able to talk to them. You'll be able to surround them. You can press the tubes. They do the same thing at both places when you press the tubes because all their blood is running out into these machines and coming back. And then we have the final, which I have no control over. It's June 10th, Tuesday. And we have the last 2 lectures, Friday and Wednesday. Well, not exactly the last 2. There's one in between. But 2 of the lectures are pre-final problem sessions. So we'll work even more problems for you. And hopefully by the time you arrive at the final, everything will be cool. So here's, again, the TAs. And here's the references 1 through 8. These are the books in the library. And the library is the Swain Library, which is about 50 feet from here. Okay, so any questions about that? So this is all on Courseworks. So the whole schedule is laid out before you. You know what your life is going to be like, and you should be very happy about that. I will now shut this down. Red, you said something about get a real computer, wasn't it? No. Okay, C, Theo, C. That really hurt me. Yeah, that's the idea. Well, it's all right. There's still D and F to go, so you don't have to worry. What's this? Yeah. Who said that? It's an oil rig. Anybody have any idea where that oil rig is located and what year this picture was taken? Pennsylvania. Where? What city? This is like trivia. Come on. Starts with a T. Ends in Ville. Anyone from Pennsylvania here? Anyone admit to being from Pennsylvania here? Titusville. Titusville, Pennsylvania. And this picture was taken on August 28th, 1859. And the person here is Edwin Drake. How many have heard of him? What do you know about him?
Founded a big oil company.
Founded a big oil company. But that's okay. At least you had the... Oh, by the way, this is a very safe class. So when I do the Socratic thing and ask a rhetoric question and there's no answer, I just sit here until someone says something. We sit here all the time. So it's a very safe place. Even if you're not sure, and we may laugh at you, don't take it personally. Nothing's personal in this class. We're going to have fun. I mean, you know, do your best and participate, and it'll be a lot better. We'll have it. This guy's Peter Wilson. He's actually Edwin Drake's druggist. And apparently this is also a picture of one of the first drug deals going on. You see his pants are full of something here. We're not quite sure what's going on. And then there's these three stooges back here. And this is a derrick. So what happened in Pennsylvania is people had noticed sort of black stuff coming to the surface of the ground. And they also found out if they lit it on fire, it would burn. And so he went poking around to see where this stuff was coming from. And that was the first oil well. And of course, this was, in a sense, the beginning of chemical engineering. Because chemical engineers originated, if you will, as a species to basically take oil, which is a very, very complex set of nasty molecules, and refine them into liquids and gases that are of use in society. Could be methane, propane, ethane, butane, pentane. Finally, when you get to heptane and on up, these things start becoming liquids at room temperature. And they found out that if you took this stuff and boiled it, you could fractionate it into gases and liquids. The liquids could be used as fuels, and the stuff that was really nasty, the tar, could be put onto roads. And this gave rise to this profession of chemical engineering as the people who refine oil. Now, I would have to tell you that probably in the last 20 years, not one of our undergraduates has gone into the oil business. So this is how it started, but we've transcended that. It's not that we don't refine oil anymore. I mean, we do, but we've pretty much figured out how to design oil refineries, essentially using software and computer programs that have embedded in them the smartness to handle a variety of crudes and to produce products over the year that meet the market demands. And so as you'll learn on Friday, during the summer, the refineries are making heating oils for the winter, and during the winter, they're making gasolines for the summer. And so the crude oil stream comes in, and it gets changed molecularly into products that meet the market demand. Now, that's not to mean that to demean refineries or to say it's a bad idea to go to work for an oil company, but Few of our graduates tend to do that, and I'll talk about some of the other places where they do go. But that's for historical purposes. So what is chemical engineering? It really is taking basic sciences, physics, math, chemistry, and now biology, and applying them to the conversion of raw materials into valuable products. So it started out with crude oil into valuable products, doing it with a respect for the environment, which I can tell you was not in the picture for many, many years. In fact, we're still litigating, and I do participate in litigations of people who behave poorly in how they disposed of materials even as late as the 1980s and early 1990s, thinking that the world is a wastebasket. It can sop up anything we throw into it. That's just simply not the case anymore. And chemical engineers design and manufacture useful products. And this is done through chemical reactions, making and breaking chemical bonds. And usually when I get to this point and talk about catalysis, accelerating chemical reactions, and separating and purifying things, people get scared. They ask me, is there any chemistry in this class? And my answer to that is, what don't you understand about the word chemical engineering? I mean, it's sort of like taking an English class and learning Spanish. I mean, yeah, we're going to talk about chemistry in here. Is it deep chemistry? No, it's not going to be deep chemistry. It's something that you can all handle if you've got at least 3 fully simultaneously functioning neurons at any given point in time. So what do I mean by converting raw materials into products? I'll give you some examples. We talked about crude oil. There are refineries in the North Bay here, up by Martinez, if you're familiar with that area. There's also a big one along Highway 80, just north of Berkeley. These will deal with on the order of about 100,000 barrels a day of crude oil coming in, running 24 hours a day. Does anybody know how many gallons are in a barrel? Okay, 55 in the kind of barrel that you normally see. But unfortunately, that's not a barrel of oil. And don't ask me where this came from, but it's 42 gallons. So you're looking at 100,000 times 42 in terms of the number of gallons that a modern refinery will handle. Some go as high as 250,000 barrels a day. There's one refinery up in Benicia where the ships come in and unload directly into the refinery and they process it. They don't even have storage for it. Can you imagine running a business like that? What if the boat doesn't come in or it hits something? You're in bad shape. But things like that don't tend to happen very often. So they make gasoline and jet fuel and monomers. And you might say, where does all the jet fuel at San Francisco Airport come from? It comes from these refineries. But you don't see trucks coming in. There's pipelines that go under the bay that carry jet fuel from the refineries directly to the airport, puts it into underground tanks, and the jets are fueled. Jet fuel is really nothing more than kerosene, basically. It's a certain boiling fraction of crude oil. That means that it boils at a certain temperature, and jet engines are designed to accept that kind of fuel. We can also make monomers, and monomers are basically small molecules, say like ethylene, and if you start attaching them to one another, many ethylene molecules, what do you think you get? Polyethylene. You don't get the bottles right away, but you get the polyethylene, which you then cast or mold or blow mold into bottles, milk cartons, or whatever. If I take polyethylene, which is nothing but carbon with hydrogens hanging from them, and I replace every other hydrogen with a chlorine atom, I get polyvinyl chloride. If I replace every other one with a benzene ring, I get styrene. If I replace all the hydrogens with fluorine, I get Teflon. So it's kind of cool, isn't it? I mean, this is how you get all these things that you hear about, all come from these monomers, which get attached to each other like chains, like a railroad in a railroad car. So that's how you get, oh, I see polyethylene's up there. Shoot, and you got it. I can see now why. Okay, so silicon crystals. You probably don't realize that at Intel, who do you think Intel hires? What kind of disciplines? EEs, double E's, right? There's more chemical engineers working at Intel than there are double E's. In fact, Andy Grove was a classmate of mine, and he was president of Intel for many years. And why on earth I didn't go with him? He's living up here, big house. I live down here in a drain gutter. I mean, it's awful. And so, Andy Grove understood things like diffusion and reaction and chemistry, and was able to help develop the technologies to grow very large, up to now 12-inch pure silicon crystals that are then cut into wafers, onto which you impress the architecture that results in the transistors that basically are collected together. And that's, of course, the double E's domain. The double E, if you will, sort of the architect of what gets imprinted. The chemical engineer provides the framework on which this can be drawn and then does all the cooking. In other words, these things have to be doped and they have to be chemically reacted in order to finally get a chipset out of it. Inorganic materials, which are basically non-carbon containing materials, result in such things as ceramics. And other raw materials, such as glucose or sugars, can be converted through biological means using microorganisms into things like pharmaceuticals and fine chemicals. And this is becoming a very, very huge industry, particularly since recombinant DNA happened in the early 1970s, where we now have control over the genome, and we can take microorganisms that are surviving out there in the dirt, and we can coax them to make interesting chemicals that they otherwise wouldn't have made, because they just didn't evolve to make those things. But we can use them as basically little engines, little machines, and when you can grow trillions and trillions of them in a test tube, you can generate a lot of production capacity. Many of our students now go into, besides refining or petrochemicals, which is polymers production, of which is still a very robust industry, is protecting and improving the environment. So one is, after you destroy the environment, then you come and you fix it up. So there's two things you want to do now. First of all, don't destroy it in the first place, but if you happen to, chemical engineers are very much involved in what's called remediation. And one of the things that we have real problems with is people have, over the years, sort of just hawked out into the ground, or they punch a hole in the ground and they dump everything in it that they don't want. And lo and behold, it gets mixed up in the groundwater. And then someone over here drills a well, build a nice little house, they drill the well, the kids come drink, the kid goes, eh! And what happened? Well, the kid just drilled into this chemical cesspool. And the kid didn't drill it, the kid drank from it. And it's bad. And so how do you clean up groundwater? I mean, you got billions and billions of water flowing in places you can't even see it, and it's chemically contaminated. And so it's a real interesting problem. I'll talk about that toward the end of the class. Degradation of toxic waste in the airshed. So you all have catalytic converters on your car, or you should. And these are essentially little chemical reactors that take unburned hydrocarbons, change the nitrogen oxides, reduce essentially the pollution capacity that's coming out of the back end of a car. And zero emission design, this is really driving all new design now. The first one I did was probably 1985. It was about a $140 million paper processing facility near Centerville, Ohio, for any of you that are from Ohio. It's near Granville, near Dayton. No one's from Ohio, okay? So the idea here is you couldn't build this plant unless the only thing that the plant released was water and nitrogen and oxygen. So anything that came in had to be converted, and any waste product had to be degraded to that level. That made it a real interesting design problem. So we're involved in all kinds of manufacture of useful products, whether it's biomedical devices. We'll talk about artificial kidneys. There's artificial hearts. There's vessels. We'll see some of those. Probably not so much we used to in the artificial kidney center. They would implant vessels under your arm so they could hook the machine up to it and not have to use your own vessels. They'd hook this fake vessel up to your arterial and venous system so that essentially you had a vessel very close to the surface of your arm. It kind of bulged, looked like a little tube here, and then you could stick needles in it and get the blood out. Chemical plants, whether it's paper, big industry, plastics, refineries, we've talked about that, pharmaceuticals, of course, fertilizers, pesticides, herbicides, you name it. We're involved in the electronics industry. I've spent a big part of my career designing diagnostic devices. First one I did was a pregnancy test kit, and that was a really interesting engineering problem because it was really low-hanging fruit. Because when a woman gets pregnant, she puts out a protein, human chorionic gonadotropin, in big amounts start coming out, literally hours after conception. So why not see if that's changed? And it was so funny because when we went into the design team, you get all these geeks together and they're saying, well, how much should we measure? How much should we measure? I said, look, it doesn't matter. It's binary. How pregnant can you be? I mean, you're either pregnant or you're not pregnant. It's a binary thing, so it's an easy device to make. If it's there, it's there. If it's not there, it's not there. Hey, let's go design that thing. It was a big market. We now have diagnostic devices that actually measure amounts. We put one together for 7 drugs of abuse. It's used in practically every police station in this country. You come in and they think you're high on something. They'll ask you to pee in a little cup, pour it on our little device. Boom, right away, we know if you've been smoking marijuana, if you're high on coke, if you've got methadone, you got everything in you. It's good, we know everything. And it's a lot of fun to make these things. And you might say, well, chemical engineers don't do things like that, but in fact, we do. Novel materials, polymers, biomaterials, nanostructures, composites, make batteries and fuel cells, a lot of control and monitoring systems. The whole food industry, some people don't think about it. What do you do when you cook? That's chemistry, right? You're in there, you're heating the crap out of something. What do you think's happening to it? I mean, and a lot of it's irreversible, right? You fry an egg, does it ever go back to the yolk? Huh? Crawl back in the shell? No, it doesn't seem to do that. You know, a lot of this stuff's irreversible. And, but there's a lot of chemistry that goes on there, and in pollution control devices as well. So there's lots of opportunities as a chemist. And when I was your age, way back in the Jurassic Park days, I went into, I was a lost soul. I started at Berkeley in the early 60s. I got accepted to 2 places. I got accepted to Stanford and Berkeley. And I had this really good, tight-knit group of my high school buddies. Not one of them got into Stanford, but we all got into Berkeley. And the problem was this SAT. You ever take the SAT? In those days, your mother would wake you up, hey, what's going on? He says, take this number 2 pencil and go up to Eagle Rock College and take this test. I don't want to take any tests. It's Saturday. You got to. It's the SATs. You got to get into college. I went up there at about 11 o'clock in the morning. My pencil broke, so I left. And that was my SAT. No Princeton review, no nothing. I didn't even complete the friggin' exam. And I got into Stanford. It just shows you things are a little different these days, And so I said, okay, I'll go to Berkeley. I'll turn Stanford down. I'll go to Berkeley. All my buddies are going to Berkeley. And slowly but surely, they started flunking out. And the other problem is I didn't realize that Berkeley was a land-grant college, so I had to be an ROTC. Well, this is the friggin' Vietnam War. I didn't want to be an ROTC. I was an anti-war. I was a pacifist. So I ended up, what did I do? I tried to get in the Army band. But the only instrument I played was the accordion and the piano. And so they didn't want a guy with a piano on his back walking around. So that didn't work. So then I burned my uniform and then took my M1 gun and shot out all the lights at the gunnery range. And then actually started shooting at some of the people. And so they kicked me out. I got 4 units of F on my transcript. And out of 8 semesters at Berkeley, I only have 4 where I got grades, because the other 4 we were all on strike or in Washington protesting the war. It was a great time, good music. And college, I know, is a little different these days for you folks. But it was a good. Where am I going with this? What did I start out with? And so anyway, I went to Berkeley, and then came to Stanford. The war was still going on. I was about ready to get drafted. A couple profs from Berkeley had been hired into the Chem E department here at Stanford. The Chem E department had just started. They called me up and they said, hey man, hey dude, what are you thinking about? And I said, well, I'm thinking about staying out of the war. And they said, why don't you come down and keep your student deferment? I said, how do I do that? Well, let's go to graduate school. I said, okay. So I went to graduate school. And this isn't a wonderful story. But, it kept me out. But then I graduated in '69. The war's still going on. So now the draft board's after me again. So I moved to Europe and then hung out naked down in Crete for many years. It was a lot of fun. Then came back and got a job at the Denver Research Center of Marathon Oil Company. The only reason I picked them is because they're located in Denver, and I love skiing. I got fired after 4 weeks because I never showed up. It was a great skier, though, let me tell you, man. You just get up every morning. I got 2 choices. I go to the Rockies, or I go into this dump and work. And so then I figured I have this problem. I can't really work for people. I can't work for anybody. So I decided to go to med school and be a doctor, because in those days, doctors, were on their own. They're not controlled, as they are today by HMOs and other people. And so I got accepted to the University of Colorado Medical School, and sure enough, Stanford, the department who knew me because I got my PhD, called me up and they said, hey, we hear you're going to medical school. How are things going? Yeah, I'm going to medical school. My job didn't work out too good. And they said, would you come to Stanford and start a bioengineering program? What? I said, sure. We're on the way. We literally packed and drove our '65 Mustang across the country and came right here. Little did they know I'd never had a course in biology or biochemistry in my life. So I had to start reading books and sort of get, up to speed, as it were, because I was the bioengineering guru. And again, things like that don't happen too often much anymore. And then I had just happened to start working with Stan Cohen in the medical school, because he's the only guy that would talk to me because I was an engineer, and our recombinant DNA happened in our lab. So how's that, watching it happen in the bench next to you? And then, that was the end of the game. And then somehow they managed to give me tenure. Well, all I can say, it's a flawed process. We don't always get it right. So let's just finish up talking a little bit about the course, if you're still interested in it. On Friday, we're going to talk about process flow diagrams. Your first problem set happens to be involved with process flow diagrams, and it's already mounted on the website. You can take a look at it, but I'd suggest I'm going to suggest don't really start working on it tonight, because I know how excited you are. Wait until at least Friday, which probably translates into Tuesday night. But anyway, you'll have the equipment that you need after that. So a lot of this class is built around conservation principles. We conserve things like mass, and we conserve energy. I'll teach you how to do that. There's going to be a little bit of chemistry. There's going to be some physics, and there's going to be some biology. And I'll try to show you how you can interlink these together and do some cool things. As I said, the whole class is built around, I think the fun way to teach it, I don't know if it's the fun way to learn it, but if I have a book and I've got to go through, why is that bad? Well, I didn't write the book, and then maybe that's not the way I want to do it. So I have a choice, write the book, so I sort of wrote a book, and do it my way. And my way is to build it around design. So we're going to design things. We're going to design an apheresis machine, an artificial kidney. We're going to design a high fructose corn syrup plant. But all the while, under that, you'll actually be learning something. It's subliminal. How do you say it? Subliminal. Yeah, how do you say it? You say it like I do. You've got a mouthful of oatmeal just like me. So these case studies that we're going to talk about, first one's going to be a platelet donation machine, apheresis machine. This is the best I can do with the programs I have on my computer. But you get it. And we're going to talk about high fructose corn syrup. That's corn going into a bottle of high fructose corn syrup. We're going to talk about pharmacokinetics. This is a nicotine patch on this guy's arm. And, you know, I don't know if you've had classes, what I call the PowerPoint mania classes yet. The prof gets up, and it's how fast he or she can switch the PowerPoints from one to the other, and you just sit there, you know, and you're sort of blitzed. You can see I'm using old technology. This is the last overhead projector on the campus, and I'm the only one who uses it. I asked my assistant to make an overhead for me this morning, and she quit. So it's just one of those things. I ran out of things to talk about. Look at that. 5 after 3. The class begins. When? And when are you going to be in your seat?
2:30.
Yeah, I know, Theo. D. So let's just start putting minuses. F minus, F minus, minus. So we'll make an agreement. You get here on time, I'll quit on time. You like that? All right, so we'll do that. So check out the website. And, oh, by the way, there are going to be some times you show up and I'm not here, but that means there's nobody here. There's about 3 or 4 times where actually I have meetings with the National Academy of Sciences in Washington. They don't seem to care that those of us on these committees have day jobs. So Max will come in occasionally. When Max comes in, I don't want you to get up and walk away. Max doesn't like that. Max will deliver the lecture on that day. There aren't too many of those, but there will be a few. So don't be surprised. Other than that, take advantage of the TAs when you get desperate, or even when you're not desperate, because they are, and they need companionship. That's why they're doing this. All right? See you on Friday.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.